VisualCAM 2017 for SOLIDWORKS is a gold certified CAM product. This runs in SOLIDWORKS versions 2010 all the way up to SOLIDWORKS 2017. So if you're running any of these versions from 2010 and up for SOLIDWORKS, you will be able to run the VisualCAM 2017 plugin in SOLIDWORKS. Now today, we're going to start with our brand new enhancement, which is feature detection and machining. And we're going to go over that in SOLIDWORKS. And I'm currently running SOLIDWORKS 2017. So as you can see, VisualCAM 2017 runs in SOLIDWORKS 2017 and older versions of SOLIDWORKS going all the way back to 2010. Now we do have for both 32 and 64-bit versions for SOLIDWORKS. Now I have a part that's loaded, and as you notice, when VisualCAM plugin is installed and loaded, you'll see a VisualCAM 2017 tab that shows up under the Command Manager in SOLIDWORKS, and the VisualCAM's CAM interface appears as a tab right next to your Feature Manager design tree, so you can switch back and forth by just single click of a button. You have the Machining Operations browser, which appears over on the top half of the browser window, and the lower half includes the Machining Objects browser, which has tools, machining regions, features, and knowledge bases. Your workflow would be typically going from left to right as you work through each of these groups under the Program tab, and then you switch over to the Simulate tab to run verification. So to detect features and be able to machine these features, I would go over to the Machining Objects browser and then click on the Features tab under the Machining Objects browser and select Create Machining Features. I'm going to select the face of this part and pick OK to accept it, and you'll now notice that the features are being detected, and the detected features automatically appear under the Features tab in the Machining Objects browser. So the feature detection and machining, in this case, we're working with the prismatic part. You'll notice that several different feature types have been identified. We have a planar face, we have prismatic pockets, which has identified all of these pocket features, and we also have a hole feature in here identified. There are several feature types we detect for both 2.5 axis and also 3 axis. I will give you an overview of all the different feature types we currently detect. Now once we have these features detected, you could program toolpaths by right-clicking on a feature and the feature tree and selecting a machining operation. So I'm going to choose facing, and you'll notice that the feature is automatically added. We'll make a selection for the tool, specify the parameters, and then generate produces the toolpath. In the next step, I would like to program these pockets. So select the prismatic pocket features, right-click, and I'm going to choose pocketing. So depending on the feature type, you'll notice that the operations that are available to you are automatically filtered. So for a pocket, you could either do a pocketing or a profiling operation, and if you have an open pocket, you could also do a facing to program an open pocket. So those are the 3 different operation types for prismatic pockets. You'll notice that all of these features have now been selected. We'll make a selection for the tool. We'll establish our cutting parameters in here, and then choose Generate. So the toolpath for the prismatic pockets has now been generated. Finally, I would like to program the hole features. I'm going to select the hole feature in the tree, right-click, and choose hole pocketing. So if you'd like to do drilling, a pre-drill operation, you could do drilling first and then do a pocket. So in this case, I'm going to go directly to a hole pocketing operation. The hole feature and the hole cross-section is displayed under the Hole Features tab. We'll make a selection for the tool and then pick Generate. Now you'll notice that with the feature detection and machining, all of your parameters in here, like the hole depth, all of this is automatically established based on the feature that's being identified. So this saves you time in having to go in and input these parameters as they're detected based on the features automatically. So we now have programmed the part with 3 operations, the facing, pocketing, and hole pocketing after identifying these features. Now once I have these operations programmed, I'm going to go over to the Simulate tab to run a verification. So I'll switch over to the Simulate tab. I currently have a stock model defined in here. I'm going to select the operation and click on the play button to run a verification. So now we have successfully programmed the facing, pocketing, and hole pocketing. Finally, I could also add a profile to relieve the material from the stock. So I'm going to go back to the Features tab, select the planar face, right-click, and I could choose Profiling, and the feature is automatically added. Now, if you'd like to specify any of the parameters like your finish depth per cut, any of these steps in here, you can specify also, and also specify your depth per cut, and then pick Generate. So profile pass is now added. I could run a verification of it from the Simulate tab. So these are one of the ways of identifying features and machining it. The next example I'm going to go over is detecting features of additional feature types. And in order to do this, I'm going to bring in another example. In this particular step, we will be identifying slot features on this part. So you notice that the part here is a prismatic part. You have two slot geometries for each feature in here, and we'll go ahead and identify these slots. So the steps are very similar. We'll go to the Features tab under the Machining Objects browser and click on Create Machining Features, select a face, and accept it. So you'll now notice that the planar face feature has been detected and all of the slot features have been identified. So there's a total of 8 slot features being detected right in here. And as you select each of these slot features in the feature tree, the corresponding feature is now displayed, previewed on the graphics screen. Now, if you'd like to program the blind slots in here, you can just basically select the features from the feature tree, highlight them, right-click, and you'll notice that you can now select slotting. So the slotting is a new operation type that's offered in 2-axis machining operations. And the feature detection machining and the slotting operations are offered in our mill configuration starting with standard. So if you're running standard, expert, professional, or even premium configuration, you'll have access to feature detection machining and the new 2-axis method for slot machining as well. So I'll make a selection for the tool and then choose Generate. Now, depending on the slot width and the tool geometry that's selected, you will notice that in the case where the slot width is larger than the tool diameter, the toolpath generates is a trichordal toolpath with constant tangential arcs. In the case where the width of the slot equals the tool width or the tool diameter, you would create a single pass slotting operation. So I'm going to pick a tool, use the same tool in here, and then select Generate. You'll notice that in this particular case, the cutter diameter is 1/2 inch, and so is the slot width. So there's a one-pass cut pattern that's generated for slotting. Now, the slot machining, you can also program this in the traditional way that you've been used to programming by going up to 2-axis machining. You could select slotting, and you can choose select curved edge regions and select either a sketch, or you could select a chain of edges by graphically selecting those from your graphics screen, and you can make a selection for the tool and generate it as well. So 2-axis slot machining is now available in version 2017, and it's included starting with the standard configuration of our mill module. Now we've identified closed slots in here. Our feature detection and machining can also detect and identify open slots as well. So I now have an example in here which demonstrates how to program open slots. The process is very similar, so we'll go to the Features tab under the Machining Objects browser. Now, if for any reason you're unable to view the Features tab, you can click on Tools and Machining Objects to toggle the visibility or the display of the Machining Objects browser. We'll now go ahead and click on Create Machining Features, pick the face, accept it, and the slot features are now identified. In this case, it's an open slot. We have these slots identified. Right-click and select Slotting. Make a selection for the tool. Generate. Now, in the event where the tool diameter is smaller than the slot diameter, I'm going to swap the tool out in here. Use an 1/8 inch as opposed to be using a 1/4 inch. You'll notice that you can drag and drop tools from the Tools tab over to the machining operations, and as you make a change to the tool, the operation is flagged dirty, indicating that you made a tool change which requires regeneration. So you can right-click and select Regenerate to update your toolpaths. And it produces the tricaudal toolpath as the tool diameter is smaller than the slot width. If you'd like to add additional passes in here, you could always edit the operation, and under your cut levels, you can specify your depth per cut to create multiple Z levels, multiple cut levels. Now, as you can see here, we can identify hole features, closed pockets, open pockets, non-prismatic pockets. This would be requiring you to program a 3-axis operation. We could identify boss features, through slots, through T-slots, prismatic slots, and planar faces. So these are the different feature types that can be identified and machined using feature-based detection and machining. Now, the next thing I would like to go over is some of the enhancements that have been made in 3-axis toolpaths in here. So for this, I'm going to go ahead and open up a part. Now, under 3-axis machining, we've now introduced the ability to select part surfaces for machining. So rather than having to create additional machining regions by creating sketch geometries from the solid model, or having to go create additional curve regions or sketch regions, you could now select part surfaces directly from your 3-axis machining operation. So if you select a machining operation on a 3-axis, you will now see that under Control Geometry, a new tab for part surfaces appears. Now, in here you can make your selections. You can click on Select Surfaces, and you can pick the surfaces that you'd like to program. So in this particular case, I'm selecting these 2 surfaces in here. I accept my selections, and in the next step, I'm going to make a selection for the tool. I'm going to go with a 1/4 inch ball mill, and then pick Generate. Now, you'll notice that by default, the surface selection, the surface extent condition under surface selection part surface is set to on condition. This means the tool will stay on to the extents of the part surface. Now, you have the ability to go past, extend past it. Rather than having to create a curve and offset it by the tool radius, you could set the condition to be passed, and generating a tool path, you'll notice that it'll automatically extend past it, so extend past by the tool radius. And it also checks against the adjacent surfaces, so the tool path will never cut into adjacent surfaces. So we have 3 different options. You can do on condition, where it stays up to the geometry. 2 will stay completely inside, and then go past. In this particular case, using past would be more ideal for programming a feature like this. Now, a good example for programming it for a 2 condition would be inside this cavity area in here, where I'm going to go into part surface selection and pick these surfaces. make the selections, accept your selections, and change the surface extent condition from past to to, and then select generate. So this eliminates the need for you to having to create additional curve regions or sketch geometries in SOLIDWORKS to create these boundaries and select them for containing your toolpaths. You can now take advantage of the part surface and specify the surface extents under the part surfaces tab to either on, to, or past to establish your containment boundaries. This is also one of the new features and enhancements in version 2017, and this is also available starting with our standard configuration. So if you're running standard, expert, pro, or premium, you could take advantage of this. Now, earlier we were talking about feature detection and machining. Now we could also identify and detect features in 3-axis as well. So if you go over to the Features tab,
I want to interrupt a bit here and then go back to your surface selection, and I wanted to emphasize one little feature of the surface selection function that we just added. When we use the surface selection and do machining, the cutter actually checks against all the other surfaces around it, so there's no danger of gouging the other surfaces. So that's an important point that we have to emphasize here over there. Do you have an example that you can show for that?
Yes, Joe, I believe so. So I pulled in the same part that we were demonstrating for the surface selection. And I'm going to set the condition to be passed. And in this particular case, as you pointed out, it is checking against all of these adjacent surfaces in here to ensure that the tool isn't gouging the geometry, the toolpath isn't gouging the geometry. So the feature detection we talked about, it's not only applicable to prismatic parts, but you can also use for parts where you have cavities. So if you have a part similar to these where you have cavities on the model, you could use your feature detection to identify those features. So you can pick a face, and this would identify your planar face and the pocket features from the model. Now once you have these features identified, you could program 3-axis toolpath. So as you right mouse button click on the feature, you'll see all the available operation types. And in this particular step, I'm going to start with 3-axis roughing. The pocket feature is automatically added, and also it establishes a containment boundary for it. All you got to do is make your selection for your tool and then pick generate after you establish your cutting parameters. So you don't have to go through the process of creating any additional boundaries, any containment regions. The feature detection automatically takes care of all of those. So your roughing operation has been programmed. You can also view the toolpath as you step in levels. And to program a finishing operation or a pre-finishing, right click on it and choose the operation that you'd like to program. So in this particular case, I'm going to choose parallel finishing, establish a tool for it, and establish your cutting parameters, like your step over, your cut directions, and then generate. So this would produce the finishing toolpath. Now while we are looking at this particular 3D cavity pocket example, a couple of things I would like to point out here are the enhancements in 3-axis operations. Now as you take a look at the cut parameters tab, you will now notice that a new option to automatically use a facing cut pattern for core region has now been added. So when this is selected, there's an additional tab in here where you can establish your cut pattern for core regions, and for cavity regions you can establish the cut pattern. And you'll also notice that the high-speed cut pattern has now been introduced in the 3-axis roughing methods as well. So you could select high speed as one of your choices for cut pattern for cavities in 3-axis roughing. And selecting generate will produce the high-speed cut pattern for cavities areas. So the cavities and the chords are automatically determined based on your part geometry, and you'll notice the high-speed cut patterns being generated for 3-axis roughing operations. Now the same option to be able to select high speed is being unified in our 2-axis methods as well. So if you go to 2-axis pocketing, we used to have the high speed pocketing as a separate method. It's now being unified as part of the 2-axis pocketing. So you will now be able to select the high speed cut pattern in 2-axis pocketing as well. So the 2-axis pocketing offers a variety of different cut patterns, including high-speed cut patterns. I'm going to go ahead and run the simulation in here, and this produces the high-speed cut pattern. You can always toggle the visibility of the toolpath on and off. So there's the high-speed cut pattern, simulation in progress, and it's applied for each of those cut levels. And you can also view the toolpath as you step through each of these cut levels. So it starts out with a spiral pass and then creates constant tangential arcs. So going back to some of the other enhancements we were talking about in 2-axis, the 2-axis roughing method also offers the same option similar to the 3-axis roughing, where you can choose facing cut patterns for core regions, and you also have the option to set the cut patterns for core and cavity pocket regions, and the high-speed cut pattern is also an option in 2-axis roughing as well. So these are numerous enhancements that have gone into our 2017 version in 2-axis and 3-axis methods, and you'll notice that the high-speed cut pattern is now offered in 2-axis roughing, 2-axis pocketing, and 3-axis horizontal roughing as well. So now these features are available in standard, expert, pro, and premium configurations of our mill module. Now we've also introduced high-speed loops in 2-axis facing and pocketing operations. So I'm going to go over to give you an example for that. So I'm going to choose facing, and in this particular step I'm going to pick the loop around the exterior of the part in here and accept the selections. We'll make a selection for the tool. We'll establish the cutting parameters, and under advanced cut parameters I can now choose perform cut rounding, and I can specify a radius in here. Now setting a radius and generating the toolpath will produce loops, and in this particular case I'm going to switch over to the lace cut pattern in here and generate the toolpath. So you'll now notice that the high-speed loops are being produced as it transitions from one step over to the other, and this is offered in both facing and in pocketing operations. And this is also available starting with standard configuration of our mill module. This is also one of the enhancements that have gone into our 2017 release. So the next thing I would like to go over is enhancements to 4-axis machining in our mill module. We've introduced a brand new machining method known as drive surface machining, and this method is offered in our 4-axis module. So if you have expert, pro, or premium configuration, you can take advantage of 4-axis drive surface machining, or also known as true 4-axis machining. Now the part I have in here shows there are features that are dipping below the rotation center in this part. Now, these class of parts or parts similar to these can be efficiently machined using 4-axis drive surface machining, which we were unable to do it in the earlier versions. Now, this option can be found under the 4-axis methods, and you'll see this brand new method called drive surface machining. So as you select the drive surface machining, you can now select these surfaces to be machined. So I'm going to click on select surfaces and pick these surfaces. Graphically, you can select those surfaces. And you can also ensure to make sure that the surface normals are oriented correctly. So in case you need to reverse the normals, you could always select and hit the flip active normal, or you can flip all the normals in here. The next step is to identify a tool for this process in here. So I'm going to use a ball mill. Establish your feeds and speeds, your clearance, and then finally your cutting parameters. You can choose to go along or across axis, and generate computes the 4-axis drive surface machining toolpath. So the tool remains normal to the surface being machined in the case of drive surface machining. So you end up with a true 4-axis toolpath where you have 3 linear axes and a rotational axis. Now let's run a verification in here for the drive surface machining toolpath. So this method is offered in our mill module, starting with our expert configuration of the product. So this is true 4-axis machining, also known as drive surface machining. Now the next thing I would like to go over is one of the newer enhancements in 4-axis machining as well. This method is known as rotary instancing, or also you could call it repeat indexing in 4-axis. Now again, this method is also available starting with our expert configuration of the mill module. Now the part I have shown here has features, identical features that repeat itself in a pattern, as you can notice it. So rather than having to program each of these features and create a rotate table operation and repeat them for each of these faces, you could now take advantage of rotary instancing. Now in this particular example, I have a facing operation, a profiling, and a drilling operation. So I've programmed 3 2-axis operations in here, and I would like to repeat those or index them across the entire part. So with our 2017 release, you could now take advantage of this feature called rotary instancing, and you can specify the incremental table rotation angle and the number of repeats, and then select generate. So this creates a rotary instance folder. I could now select all of these operations in here and place them into the rotary instance operation folder. So you'll now notice that as I select the rotary instance, the instances are created for each of the features and they're being repeated. You could also perform a cut material simulation for each of these instances. So this rotary instance feature can be used in combination with 2-axis, 3-axis, and even 4-axis operations. So if you had a 4-axis profiling or a pocketing or even a parallel finishing operation, you could apply the rotary instancing to all of these operation types. And again, this is included in our 4-axis module, which is available starting with the expert configuration.
Another point I want to emphasize here is in your facing operation, you're able to tell the cutter to come from the outside on the material, and maybe you can explain how you did that.
Sure. Thanks for pointing out, Joe. So if we have a like an open pocket in here. So the geometry, the feature what I've selected in here is actually an open pocket. So I have three sides. So when we have an open pocket, selecting two axis facing will ensure that the cutter will start from the side where it's open and will never go past, so it will treat the other three sides as side walls or part boundaries, so not to be machined away. So you can use two axis facing as a very efficient way to program open pockets. So rather than having to create additional geometries to to extend past on the side where it's open and create curved geometries, you can use two axis facing to program open pockets. So in here we have two axis facing, and you can notice that I only have three surface edges selected, which results in an open pocket, and selecting a two axis facing operation will ensure that the cutter enters past the geometry on the open side and ensures that you result in a nice open pocket machining operation. So you could use this on a normal two axis operation on a prismatic part, or you can even apply it to instances where you have rotary instancing that needs to be performed in a four axis as well. So the next thing I would like to go back and visit here is the part we looked at just a short while ago with the drive surface machining, as one of our attendees had a question about inverse time feed rate. Now this is also a enhancement that's been added to our 2017 release. So in order to be able to output inverse time feed rates, you would go into your post processor and you would set the option to output inverse time feed rate. This will be found under the feed rate section in the post process generator. You would select this checkbox and then you enter in your inverse time feed rate code. I believe G93 is to toggle it on and G94 is to toggle it off. So we set the G93 and G94 for inverse time feed rate. We'll go ahead and make these edits, save the post processor. Now as you post process the toolpaths, the inverse time feed rate will be computed and will be output on all your 4-axis continuous and also 5-axis toolpaths. So inverse time feed rate applies to multi-axis 4 and 5-axis toolpaths. And as you notice here, it starts out with the G93, which enables your inverse time feed rate, and the feed rates are being computed. You can see the feed rates are output on each line when you have a linear motion for inverse time feed rate. And as you look towards the end, you'll see that the G94 is output to cancel out the inverse time feed rate. I hope I was able to answer your question about inverse time feed rate. Now as we are on the topic of feed rates, the next thing I would like to point out here is we've introduced feed rate optimization in our 2017 release. And this feature is part of our toolpath editor, and it's offered both in our Pro and Premium configurations of the product. So what I have here is a part program with a 2-axis profiling operation. And we'll take a look at how the feed rate optimization can be applied in here. So as you double-click to launch the toolpath editor, you will now notice that under the Global Edits tab, you'll find feed rate optimization. As you select feed rate optimization, the feed rate optimization dialog provides you controls to establish feed rate direction in the corners. For example, here, I could set the distance before a corner start to reduce the feed rate. So as I'm approaching this corner, I could say half an inch before I approach the corner, I would like to reduce the feed rate to 25% of my actual cut feed rate, and reset the feed rate back to the cut feed rate after going past half an inch from the corner. So you can apply the feed rate optimizations, and you can also ignore motions if they're shorter than a certain distance in here. So you can specify these parameters, and as you accept it, you will now notice that these changes are automatically reflected here in the toolpath editor, where it drops the feed rate and restores it back in here. And as you post-process your toolpath, you will notice that these are reflected in your posted code, where the feed rate is reduced to 25% of your actual cut feed rate. In this particular example, the cut feed rate is set to 40 inches per minute, and you'll see that it drops to 10 and then restores it back to 40. So the feed rate optimization is a great new enhancement and helps you in reducing the feed rates as you navigate the cutter around the corners. And this feature is offered in our Pro and Premium configurations, and it's part of the toolpath editor.
One other point on the feed rate optimization, we will be posting a blog article on this, a little bit more explanation on how feed rate optimization works. So please subscribe to our blog if you haven't done that already. Thank you.
We've also added options to fit arcs to toolpath. This is a global option that's now available in 3, 4, and 3-axis toolpaths, and this is available starting with our standard configuration. So if you take a look at the CAM preferences, and under machining, you'll now notice that there's a new option to be able to fit arcs to toolpath, and you can constrain it to the planes. Now these are the new options that have been added in 2017 release, where you can constrain the toolpath to just an XY plane. So there are certain controllers which can only handle arcs in the XY plane but not in other planes, so you can limit those. And also you have an option to set the maximum arc radius. So if the machine can handle arcs only up to a certain radius and not beyond, you can limit it in here. Now as you establish these options in here and you program a toolpath, so in this particular case I'm going to choose a parallel finishing operation. We'll select the tool, and under advanced cut parameters I'm going to choose to perform arc fitting. And as I generate the toolpath, you'll notice that the arcs are being fitted to the toolpath in the 3 principal planes. Now if I choose to change any of the parameters in here, if I choose not to output arcs in the X, Z, or Y, Z plane and go back and regenerate the toolpath, you'll notice that the arcs are no longer being fitted, because in this particular case the arcs were being fitted in the X and Z plane, as the direction of the angle of cut was set to 0, which would produce arcs in the XZ plane. So you have the option to establish your arc fitting parameters as a global parameter and not having to go through and set it in each operation. Also, while we are talking about the machining preferences, we talked about arc fitting. There's also one other nice enhancement I want to point out here, is being able to output drill cycles as linear segments. There are numerous machine controllers that do not handle like a peg cycle like a G83 or even a standard drill cycle G81. For those machine tools, you can have the ability to output them as linear motions as opposed to outputting them as a CAN cycle. So you can choose this option and then regenerate and post a toolpath will output these as linear cycles.
One quick comment while you have that dialog open, Uday, on the arc fitting control. One of the reasons why we moved it to a preference dialog is we found that some of the machines, it's really a machine-specific property. So some machines, for instance, if you had a large arc radius, they would actually fail. When you output a toolpath and you had a really large arc radius, the machine would actually stop when it hits the arc because it's not able to process that arc. So that's one of the reasons, one of the main reasons we put this maximum arc radius parameter in here. So if you, for any reason, are finding that when you after arc fitting in the 2016 release, and you're finding the toolpath actually stops, this might be the reason. So in 2017, you can actually specify that maximum arc radius to prevent that from happening. Thanks, Uday.
Thank you, Joe. Now, while we are on this topic of preferences, I also wanted to point out there's a very nice enhancement that's been added to our 2017 release to make it easier for our users to learn and understand what each of the parameters are in the machining operation. So we've introduced what is called tool tips, and you can enable that. By default, they're enabled, which is called context-sensitive tool tips. And as you go into any of your machining operation, for example, and you hover your cursor over these options, this provides you with a tool tip describing the task that you can perform. So for example, if you go into the cut parameters, selecting hovering over cut direction will give you a description of what mixed cut direction is as opposed to climb or conventional. So this is very useful. Rather than having to go in and refer to the online help document, you could get help directly from each of these dialogues as you hover the mouse over each of these parameters. These are context-sensitive tool tips that have been made available in our mill and turn modules in VisualCAM for SOLIDWORks.
One more note about those tooltips. If you are an advanced user and you don't need to see these because they can get a little annoying if you're a very advanced user and you know how to use these things, you can actually turn these off. So Uday, please show that.
Thank you. So as Joe pointed out, the user interface preferences under CAM preferences has an option, a checkbox, to enable or disable the context-sensitive tooltips. So you can clear this out right in here if you do not want the tooltips to appear in any of the CAM dialogues. Now we've also added expressions in all of the edit boxes as you enter in your parameters. So as you go into any of the edit boxes, like for example, if you want to define a tool and you wanted to add a new tool in here, and I would like to add a 3/8 inch end mill, I no longer need to do the math to interpret the decimal value for it. I could just go ahead and enter in 3/8 and the system will automatically compute the value for you. So you can also do you can use operators like parentheses, additional parameters to do a complex expression, and the result will be displayed right in here. So this is available in the tool definition and also in all of your machining operation dialogues. So as you go into any of the operations, so let's say you want to go do a pocket operation and you specify your depth, you want to go an 1/8 inch, you just type in an 1/8 inch and you'll notice that it automatically establishes the value for you. So this is also a very nice enhancement in 2017, so it makes it easier for you to input these parameters as well. And there's also a tooltip for that. If you'd like to not have the tooltip displayed, you can go into user interface preferences and not have the tooltip for these computation being displayed on your screen. Now I would also like to point out that the expressions are also now available in the post-process generator. So if you'd like to create expressions, you can do that in the post-process generator, and this is also documented in the online help as well as in the post-process generator. So if you refer to our What's New document, I could show you a quick example of how the expressions can be established in here. So you could go in and you can use these, in addition to the variables, you can establish these expressions on it to create expressions in the post-process generator. Now, last but not the least, I would like to show some of the very nice improvements and enhancements to our simulation that have been made in our 2017 release. Now, in order to go with this, I'm going to load in one of the parts we looked at earlier, and we'll go through the simulation enhancements. Now, under the Simulate tab, in the simulation preferences, now the preferences can be invoked either from the CAM preferences or from the Simulate tab. We now have the option to display silhouette and sharp edges during simulation. Now we can select these, and you'll notice that the edges are now being displayed. You can, if you toggle the stock visibility on, even in the shaded mode or in the translucent display mode, you can see the edges being displayed around the stock. And as you simulate machining operations, you can see these being displayed as well. So the silhouette and sharp edge display option can be toggled on or toggled off in our 2017 product. And this is available to all users starting with standard configuration. Now this is one of the many improvements in simulation. We could also assign colors for each operation that you're simulating. Now the colors can be set either to a tool. You can assign a color as you define tool. You can go into your tool properties and establish a color for cut material simulation, or you can assign a color to a machining operation, or just apply the texture that you enable. So in this particular example, I'm going to choose assign color based on the machining operation, and you could select the machining operation, right click and go down to properties, and you can choose a simulation color for each operation. And selecting the operation and simulating it, you'll notice it will apply colors during simulation based on what colors you set for each operation. Now we also have an option to not display the remnants during simulation, so to exclude the remnants, and this option can be toggled on by selecting remove remnants during simulation under the simulation preferences. And as you simulate the machining operation, you'll notice that the remnants are now being dropped once the simulation is performed for the operation. Now these are some of the numerous simulation enhancements that have gone into our 2017 release. And for those of you who are running Expert Pro or Premium configurations, you could also toggle on machine tool simulation. So the machine tool simulation can be found under machine tool definition. As you go over to the load from file option, you'll see that there have been several newer machine tools that have been added to the list, and there have been several improvements and enhancements to machine tool simulation. So for this particular part, I'm going to choose a CNC router, a 3-axis router as my machine tool, and you'll notice that the machine tool appears as you toggle the machine tool visibility on, and selecting the operation and running a simulation performs it with the machine tool. So the machine tool simulation is available for 3, 4, and 5-axis simulations. I'm also going to give you a quick example of a machine tool simulation for 4-axis.
Today, one of the attendees had a question about PEC drilling simulation. Do you want to show that?
Absolutely, we'll do that, Joe. So I'm going to go ahead and pause this in here. I will switch back to the standard drill, and I'm going to go over to the drill type in here, change the drill type from standard to a deep drill, and I'll set my step increment, which is the PEC increment, right in here, and then generate the toolpath. And I'm going to go perform a verification, and you'll now notice that the PEC drilling and the brake chip, the PEC cycles, so the PEC motions are being simulated with our 2017 release. So as you see, the remnants are being removed during the simulation process. Well, let's go ahead and take a look at the 4-axis machine tool simulation. So going back to this part where we program the drive surface machining toolpath, we'll go to our machine tool definition, and we can select load from file, and we can pick any machine tool from the list here. I'm just going to go grab one of these machine tools, and you have the option either to display the machine tool housing, or you could toggle it off right in here if you do not want it to display, and go over to the simulate tab, and selecting play performs your 4-axis simulation with the machine tool. And you could always toggle the display of the machine tool housing back on by going over to the machine tool properties and continue along with the simulation.